In this video, we're going to go over laboratory exercise M07, which covers the topics of Intel x86 32-bit architecture and opcode analysis that we already covered in our instruction set architecture design presentation. So this is our laboratory exercise, and we'll just follow closely the steps outlined in this laboratory. So the first step is that we are going to create an empty C++ project. So let's do that. So new project, and this will be an empty project C++. Okay, and of course I will use my directory structure for our course. This is going to be our directory, and the name of the project I will say M07, and we will now create this project. So we're going to add new file M07asm to the project, and I typically go into the project directory in the file manager, right click and say new folder, and add source subfolder to the project. So here we can just say new text document, right? So this is our laboratory project, and this is the source subfolder that we just created, and we simply rename the entire file M07asm. Okay, so this is fine. I'm sure it's an empty file that we just created. So now it's time to say view solution explorer, and we're going to I think the first step here, we might try to right click and say build dependencies and build customizations. So this is where we can ask the environment of this project to provide us access to MASM, Microsoft Macro Assembler. So I'm just going to check mark this option and click OK. So then we can go to source files. So this was at the project level. Once again, it was build dependencies, build customizations, and that was the access to the dialog box. Now to the source files and say add existing items, since we already created a file. And under source, we have our MASM file, which is an empty file. So right now, let's check the properties of this file. Right, so this is new file, and we're going to check the properties of this file. And since we have added this option MASM to the project configuration as one of the possible build tools to use, the ASM extension was picked up by Visual Studio Project as the candidate for Microsoft Macro Assembler build item. Okay, so this is fine. If you check the properties of your file and it says something different, like for instance does not participate in build, so that's incorrect. You then need to find Microsoft Macro Assembler on this list and make sure that it's being selected. Okay, so then the next step is simply to take this initial source file content and just copy and paste it right here. So what is curious about here is this main procedure, which contains a sequence of bytes, and a sequence of bytes using the byte directive. So the byte directive here is an equivalent of, in C++, byte is similar to a character data type, right? So I'll just switch to character data type like this. And if you wanted to create an array of characters, and I guess in C we have to give it a name, so we'll say bytes, right? Doesn't matter what. And this will be an array of 16 duplications of initializer 90H. Okay, so this is an equivalent of C++ or C declaration of a block of memory initialized with 90H, and now we're gonna have to basically run this initializer 16 times. Okay, so this is like 16 times we're going to repeat this initializer. Okay, and so this is what this byte directive allocates. Directly inside the main function, there is basically a block of 16 bytes, and each byte is set equal 90H. So I guess if you suspect that because this is our code segment and this looks a little strange inside the code segment, well, it's very likely that these encodings, 90 hexadecimal encodings, are encodings of an instruction that exists in Intel architecture. So we're going to experiment with this, but for now this is just an observation that I make about this initial setup. Now we also have 3 bytes in memory, namely under label characters we allocate 3 bytes and we store characters ABC in these bytes. The rest is the same options that we use, and at the top it says empty program that reserves 3 bytes of memory in the data segment. Okay, so very good. Let's save this. It looks fine. And then the next step in our laboratory is to click the Build menu, Configuration Manager, and change Active Solution configuration to Release. Okay, so let's do a switch to a release. Now observe it's x86, and now we're switching to the release build. And then the instruction says that we need to go to the project menu. So we can do it either through Solution Explorer or we can go through Project and M07 Properties, right? So M07 Properties under Configuration Properties. So let's take a look. Okay, configuration. Notice that I have all configurations here. Under Configuration Properties Linker, right here, Linker. We're going to specify an optimization in link time code generation, linker, and optimization, right? So linker, optimization. Notice I have all configurations. And under configuration properties, so we need to delete link time code generation. Okay, so link time code generation, what we're going to do is that we're going to say use. So I guess it may be a default option. It says leave this field blank. I mean, we could try to just delete everything from this field like this, I guess. And then in the advanced section, we need to, so again, this is the linker options, and in advanced section right here, we're going to scroll down to image safe, has safe exception handlers. It's actually at the very bottom of this set of options, right? Linker, advanced, image has safe exception handlers. We don't have any safe exception handlers in this tiny program. So we're going to change it to a no, right? So we're going to say safe exception handler no. And now we're going to apply the changes. Okay, just say okay. And let's try building this program. Okay, so this builds fine, and so now I choose to build the release build to keep it as simple as possible in terms of the image of the file. So these two options simplify code generation, and this yields the simplest coding image that the linker puts together for us when the program loads into memory. Because most of the work that we're going to do in this lab is going to be related to program that's already loaded into memory, and we're going to try to experiment with the code. Now click Debug menu and step into F11. Observe that debugger loads program into memory, opens blank console window, and pauses the execution in the main entry point. Right? So even without a debug breakpoint, what we're just about to do is to say debug and press F11, step into, which means essentially we're asking debugger as soon as any part of our program starts to run, we would like to stop and examine what is happening. So step into. All right. So what we observe is that I have these registers window opening. So yes, indeed, we have the console window created for us, and I have configured already to display disassembly. I'll just close the disassembly window for now. Okay, so now this indicator tells us that the next statement in this program is going to be this line right here, where we're just about to start execution of our main procedure. So let's click Debug Windows Modules. Debug Windows Modules. Right. So we have a display of modules. It's basically, these are all images that loaded into our program space. So modules looks like this, and so we find in this view, let's resize it just to see what's on this list of things. And so right here in this modules view, we have our executable program M07. So we have the path to this M07.exe. And so it's loaded here, and its address space occupies a certain range. I suppose it's the space reserved for the stack of our program, at least like 1 kilobyte stack is reserved over there. And so this is the set of modules loaded into our memory space. Together with M07, we have a list of dynamic link libraries which provide access from our program to Windows operating system application programming interface, API. So system functions become available to our program because these DLLs are mapped into our space. So we can start making calls here. As long as we know what calls to make, we will be able to open files, open network connections, we'll be able to browse directories. We can even start using functions to control the console window. So there's lots of functions already preloaded. That also includes creation of new processes, creation of new threads of execution, if we want to explore that functionality. So these DLLs give us access to those kinds of application programming interface. Why are there multiple modules in the view? So my answer again would be here to this first challenge, first question that we need to answer is, I'll just try to make this little illustration here, that this is a 32-bit program that we're running. Okay, so we're running this release x86 program, which is 32-bit program. A 32-bit program can have addressable space, right? This entire space from memory location 0 to memory location about 4 billion. Okay, 4 billion. So there's 4 billion bytes available in this space. Now notice that our program is absolutely tiny. We have 16 bytes and 3 bytes. So that's pretty much all we use in this program. So our program is quite tiny. It just basically takes just very little space, negligible amount of space, between 0 and 4 billion bytes available of addressable memory. However, this memory is a virtual memory. So the physical memory is basically is another layer. So behind it there is a physical layer of memory right there. Okay, so there's some kind of a layer over here behind us, and this is a physical memory. So in this 32-bit flat memory mode, the image of each application program in our operating system is using this virtual memory, and this memory is mapped into physical memory. Of course, our M07 exe is loaded somewhere in physical memory, and that physical memory is protected by the operating system. Wherever the starting address of our program M07 is in this virtual memory space, M07, right, this thing, it is actually mapped to the physical memory space. Okay, so this is how virtual memory works, and virtual memory allows us to have memory protection, so that multitasking, multiprocessing environment becomes safe for multiple programs to use, because every program thinks that it has 4 billion bytes available to its space, although it's not using all of them, but that's the impression that the system will give to each executable program on this platform, 32-bit platform. Internally, the operating system uses the CPU segment registers to securely map this to a physical space, that which is where actually in the RAM our program is loaded. Of course, in this physical memory we have already loaded NTDLL, kernel 32DLL, and others, which are components of the operating system. So these components already loaded into physical memory. So look how much available space we have over here. So what the operating system does, it maps these modules, right? It's mapping these modules, their physical memory locations, into our own memory space. So each module is basically appears as if it's being loaded by us, but it's not really being loaded by us. It only is mapped to the physical memory right here, which is already occupied by the operating system in physical memory. Again, this box is our virtual memory, which we can see if we switch to disassembly view, and you can see all the addresses that we have in that disassembly view. These addresses are these, counting from 0 to 4 billion. These addresses are virtual memory space. The physical RAM, physical random access memory, is protected by the operating system, and yes, it contains everything, but the storage of all of these things in memory is in physical memory is controlled by the operating system. We don't have that access, and that provides protection of memory. So virtual memory is a very important security feature, and this allows the operating system to control the executable environment, so that each process is giving this space and does not know about the existence of other processes unless we're going to interact with operating system components to give us information about other properties, available memory, the files that are available in the file system, and many other services that are available from these modules loaded by the system. So here you see that it's under C, Windows, sys wow 64, and these are the actual physical locations of these operating system components that are given to our program because we built it as a console application. So our console application is entitled to get access to the services that are available in these NTDLL services. So here I just want you to, in your own words, just describe why we need these multiple modules. Okay, so of course, the short answer is to be able to access the services of the operating system. The operating system puts these modules in our virtual memory space, and we can begin interacting with functions available in these modules. Okay, so this is interesting sort of discovery regarding the executable environment. In general, we say that this is our executable environment because this is what we actually have in this virtual memory, our own compiled program or assembled program in case of an assembler, and these modules that are provided by the operating system in our own memory space. And right here in this window, you can actually see the physical address ranges that correspond to these modules, including our own module. It's given sort of like a range of addresses where this executable file lives and can access this memory and do whatever we're trying to do with our executable instructions.